This edition of the Della Pietra lecture series. Jeff Weeks, our speaker today, will in fact give 3 talks. There's this one where we're going to be doing some cutting, I think, entitled Symmetry, Folding and Unfolding. Later on this afternoon at 7 p.m. This is a general public lecture, and I hope all of you will come to that. Will it have milk and cookies? I don't know. Probably. We'll probably have something beforehand, but not sure. The public lecture is entitled The Shape of Space. And then tomorrow, those of you who've managed to visualize 3-dimensional spaces, which is what we'll be doing this evening, can visualize 4 dimensions, which is a real challenge for all of us. Anyway, we're very pleased to have this Della Pietra lecture series by Jeff Weeks. Jeff was a graduate student at Princeton in the heyday of 3-dimensional topology. He was a student of Bill Thurston's. And since then, he's been studying 3-dimensional spaces, patterns, symmetry patterns in dimension 3, and how you visualize them. I know a lot of mathematicians, and I only know 2 mathematicians who have a space named after them. So there is something called the Weeks manifold, which is quite a famous manifold. It's been around for 25 years or so and has now been established to have the properties that Jeff thought it might have when he first discovered it. So it's quite a famous manifold. What? Banach spaces, yes. There's something called the Maser manifold, which is a 4-dimensional manifold. Anybody think of another space? It's got a well, Hilbert spaces, Poincaré's dodecahedral space. One of the few living mathematicians with a space named after him. All right. Well, with that, I'll turn you over to Jeff.
Okay. Thanks a lot. So I'd like to thank the Della Pietra family for establishing this lecture series and the Simon Center for hosting it. And speaking of the Simon Center, so if you talk with the researchers here at the Simon Center and you ask them about their understanding of electromagnetism, of elementary particles, of gravity, you'll find that the more deeply people understand nature, the more the idea of symmetry enters the picture, the more important symmetry becomes. Now, happily, though, you don't have to be an expert in quantum gravity in order to appreciate symmetry, and because indeed symmetry surrounds us in everyday life as well. So the purpose of this afternoon's workshop is to become more aware of symmetry. Hi, come on in for the symmetry talk. Yeah, have a seat. Okay, so first, though, before we get going on the symmetry itself, I'd like to make a little analogy here. If you want to notice and appreciate the trees around you, you learn their names. So, for example, what's this? Tree. Oh! Now the wrong audience. What? Anybody recognize this one? Yeah. Okay. So you have a maple, and these leaves are from what? An oak, and these are birches. Great. So anyhow, if you know that this is a maple, this is an oak, that's a birch, then you're more aware of these trees when you see them. They don't just blend into this generic kind of forest. Now, the same is true of symmetry. Symmetry surrounds us in the brickwork in the walls, the tilings beneath our feet, in wallpaper and fabrics in our clothing. It's all over the place, but often we don't really notice the symmetry. Our eyes see it, but our brains don't. But now, remember, with the trees, once you learn to recognize maples and oaks and birches, then you become more aware of them when you see them. And the same is true of symmetry. When you learn to recognize the different patterns, then you start seeing them all over the place. Okay. On the flat plane, there are exactly 17 possible kinds of symmetry. Here you can see an example of each of the 17 kinds. And there's a classical crystallographic naming system for these, and that system is kind of a mess. Okay, it's full of P's and M's and G's and 3's and 1's here and there in various orders. And to be honest, to this day, I still haven't learned this system because I don't really like memorizing things if I can possibly avoid it. But fortunately, in 1992, John Conway devised a much simpler naming system. Now, at first glance, it looks like I just substituted one set of symbols for another. It doesn't really look any better. But the big advantage here is that you don't need to memorize these names. You can work them out on the fly. Okay? So, yeah. So how does Conway's naming system work? The key to it is folding and unfolding. So for example, if you take your snowflake, which some of you might have made by now, you have a snowflake. Here's its unfolded form. And then we can fold it up. Which way does it want to fold here? We can fold it up to get its folded form for the snowflake. Okay? The same for the paper dolls. Here's a chain of paper dolls in its unfolded form. Then I can fold it up and get the folded form for the paper dolls. Now, the same principle works even with a two-dimensional planar pattern like this. Okay, let me just look at my notes to make sure I'm not forgetting anything. Yeah. Okay. So here's our planar pattern with the butterflies. So this is its unfolded form. To get the folded form, I'll just pick a line of symmetry, like say between this line of butterflies, fold along that. Here's another line of symmetry. I'll fold along that, fold this way, fold that way. We're almost done, but not quite, because there's still the butterfly's own symmetry. So we'll fold along that, and here's the folded form for the butterfly pattern. OK. A pattern's folded form. Hey, come on in. OK, just to recap for the later arrivals here. With symmetry, everything has an unfolded form like this snowflake, and we fold it up to get the folded form, which is called the orbifold. OK, and OK, so the 17 possible planar symmetry patterns correspond to the 17 possible different flat orbifolds that you can have. OK. OK, so we've got this nice one-to-one correspondence now between unfolded forms and folded forms. And for the names, what Conway did was to devise a naming system for the orbifolds. And then he pointed out that, well, you can use those same names, just transfer them over and use them as the name for the unfolded pattern as well. OK, so how does the naming system work? Well, whenever you have a line of mirror symmetry in the unfolded drawing, this gives you an edge of what's called a mirror boundary in the orbifold. So for example, in this symmetry pattern, you have 4 different kinds of mirror lines here, depending on which side of the butterfly you're on, corresponding to the 4 sides of the orbifold here. And in Conway's notation, a mirror boundary is written as a star. OK. And now each point where 2 mirror lines cross, okay, that gives you what's called a corner reflector in the orbifold. Okay. And so to write down the corner reflectors, what we do is for each corner reflector, we look at the number of mirror lines that cross there. So for this red one, 2 mirror lines crossed, we write a 2. For the yellow one, 2 mirror lines crossed, we write a 2. Same for the green and the blue. Therefore, the name of this orbifold is star 2222. And then the name for the unfolded pattern becomes star 2222 as well. Any questions so far?
Why don't you do star 2, star 2, star 2, star?
Ah, because the star applies to the mirror boundary as a whole. And I guess if you wanted to write star 2, star 2, star 2, star 2, you could make that your rule. But, well, actually you couldn't, because I think when you get in, this is great for planar cases, but if you got into some weird hyperbolic thing with more than one mirror boundary, then you need to know how many mirror boundaries you have.
Right, or if you had mirror boundaries and then interior points that are not mirror points.
Yeah. Okay. Any other questions on this example? Okay. No, because you can't. They have to be periodic, because otherwise you could never fold them. Okay, so as I mentioned before, you don't have to memorize the names. In fact, you don't even have to have ever even seen the names before to work them out. So I'd like to pass out an exercise here for people to get going on. Whoops. Oh yeah, there's star 222. Okay, so the exercise will be if you could group up in little groups of 2 or 3 people. The first exercise will be work out the name for the symmetry pattern on the back of this deck of cards. And I'll just send a few of these down each row here. So I'm deliberately passing out fewer than there are people, expecting that you'll be working in groups.
Oh, well, actually, there's only one fewer person here. Unless you're going to cover later about how to be in 2 places at once.
No, sorry.
That might be worth staying for that. Promise to be somewhere else.
I thought you were bolting just as the homework got passed.
Yeah, it wouldn't be the first time. There we go. And that's 3 here. There you go. Want one? Okay. Hi. And if you want, you can see the full screen pattern here if you need it. Oh, hi, Tony. How you doing? It's been a while. Here, have a seat.
Got any more handouts?
Yeah, I do. Let me get you on. People are working out. Here, you're welcome. This is the assignment is for the pattern on the back of the cards to fold it up and make the quotient orbifold and deduce its name.
No, they folded up. So when you see no more lines instead of 3, you stop.
Give me 2 markers. Yeah, just markers.
Just sold that thing.
So I see from this point, I see 4 lines. 1, 2, 3. And through this, I see. What about through here?
I think just 2 there, John.
1, 2. No, that's it. Somewhere there.
Apologize if I'm rushing some of you along a little, but I'll keep moving just so we have time for our field trip at the end of the hour. So in this picture, where are the lines of mirror symmetry here? So first I'll say there's some obvious ones that go down this 2-lane highway going this way and this way. Are there any others? Yeah, there are vertical ones here, here. Any others? Horizontal ones here, here. Any others? Yeah, the other diagonals going through the hollow circles going this way and that way. So if we advance this, so here's our symmetrical pattern, here's our orbifold. Hey, yeah, perfect. So here are all the mirror lines. Okay, now the rule is there's a mirror boundary, so we write a star. Then what numbers do we need to write after it? Yeah, and in any order, it doesn't matter. So for the red vertex, 4 mirror lines go through there, so we'll write a 4 for the red vertex. And same for the blue, 4 mirror lines, we write a 4. For the green vertex, there we have only 2 mirror lines, so we write a 2. What's the star for again? The star means that there's a mirror boundary. And eventually, I'll show you some examples towards the end here where there is no mirror boundary. Okay, whoops. So there it is. Star 442 is the name of this pattern. Like I said, technically we found a name for the orbifold, but it's used as the name for the unfolded pattern as well, the pattern on the back of the deck of cards. Okay, your next assignment, please, is to make the orbifold for a honeycomb and deduce its name.
No, but let's 2 through the midpoint of the image, 6 through the midpoint here, and then here we must have 3.
Really that much? I guess so, huh? We just do right in the middle of this. That's how far I got it. Oh yeah, that's definitely right. Look, every little piece looks exactly like that. These are the right directions for a triangle. Everything's a nice triangle. Yep.
Yeah.
There must be a 6 of them.
Listen, I don't know how
I got that. What's your pattern? The only thing you don't
Six lines.
One of those. But I think no, within that
Again, my apologies if I'm rushing anybody, but in the honeycomb pattern, with your orbifold, how many copies of the orbifold would fit into one hexagon? 6 or 12? Let's try. Okay, so there's symmetrical pattern orbifold. There are the mirror lines. Okay, so in fact we can fit 12 copies of the orbifold into each hexagon. Okay, it's got a mirror boundary, so we write a star. What number do we write for the red vertex here? A 6, because there's 6 mirror lines. For the blue one? Just 3, because there are only 3 mirror lines going through each blue vertex there. And for the green one, 2. OK, so the name, therefore, is star 632. There we go. OK, so honeycomb, whoops. So bees make honeycombs with star 632 symmetry. Okay. Escher's angels and devils picture adds a new twist to this game. Okay, it's easy to find the mirror lines here. Okay, everybody see the mirror lines in your mind? Yeah, there are the mirror lines. But what's different now is that even once you fold along the mirror lines, there's still some symmetry left. You've still got this fourfold pinwheel symmetry about that point where the wings meet. Okay, so we still need to kind of fold things up, or in this case, roll things up. And the way you can do it is, here's that square with the fourfold symmetry in it. I'll just make an arbitrary slit. It doesn't matter where I make it. And now I have to get all those wings to line up with each other. So I'll take this wing here and match it up with the next one. OK, there it goes around. OK, so we got the first wing on the second. Then that third wing will come along and line up with those two. And I didn't cut my slit very well, but you get the idea. The fourth wing comes up, and this last little bit that got cut off when I first made the slit, that comes around and lines up where it belongs at the end there. So let me stick a piece of tape on this. OK, so for Escher's angels and devils picture, this is the orbifold. Okay, this is its folded form. Okay, here it is. Whoops. Oh, I forgot to show this slide earlier. Well, there it is. So here's the orbifold as I drew it on the screen. But this is not a good picture on the screen. It's hard to take something that looks like this little coney cap thing and draw it on a computer screen. So I ask you, when you see this picture here, please imagine this. In particular, here the angel's wing looks like it's cut into 2 pieces. But really, it's not. Really, it just connects on around. OK, so what's the name of this thing? Oh, I forgot to mention where we have the gyration point at the center of the pinwheel. That gives us a cone point in the orbifold. OK, so what's the name of this thing? Well, as before, it's got a mirror boundary, so we write a star. OK, and as before, it's got this corner reflector, just one corner reflector, not 4. It's got one corner reflector, so we write a 2 up there because 2 mirror lines go through there. And in addition, it's got this cone point at the tip, so we write a 4 for that because it's a fourfold pinwheel symmetry. And there's a convention here that you always write the cone points before the star and the corner reflectors after the star to avoid any risk of confusion. OK, so
the pinwheel has to be. You have plenty of fourfold symmetry in your other patterns.
I do, but what's different here is this is the first one we've seen where there's rotational symmetry with no mirror going through it. Yeah, and all these other ones, where'd they go? There we go. Here, wherever you have rotational symmetry, there was always a mirror. And so that way we'd fold it up, and by the time we were done folding along mirror lines, we ran out of symmetry. There was no more symmetry left there. But in this example, by the time we fold it up, the folds alone only get us this far. And the mirror lines, the folding, doesn't account for that rotational symmetry. Okay. Did that answer your question? Sure. Ah, something funny happened here. Huh, I wonder what I did here. Nope. Oh, I see. It just showed the toolbar. Sorry about the technical glitch. Oh, gee, and people are leaving already. You know, I'm not sure what I did. It must have been like an open and new window or something, but I think we'll make it good here real fast. Oh, I see. It opened. Okay. Is this? Yeah. So back here.
So that's not a rotational symmetry down the middle.
It is, but it's a rotational symmetry that's a direct consequence of the reflection. So by the time you fold out along all the mirror lines, you're down to just this tiny little bit with just 1/12 of a hexagon wall, and there's no symmetry left once you've folded along mirror lines. Whereas in this case, you fold along mirror lines, and you're done folding. You're down to this. There are no more folds to make, but you still have symmetry. You still have rotational symmetry that's not accounted for by the mirrors. So that's why it's different.
The difference that you can't make a two-dimensional folded orbifold on that one? It had to be a cone?
I think there's a point of mathematical religion here, and that's about how you think of the dimension of things. And I think to a geometer that this is two-dimensional, this is two-dimensional, this is also two-dimensional, because what we really care about is this surface itself rather than the three-dimensional space it sits in. And the fact that we can't draw this one completely in a plane is kind of less relevant to the discussion.
Does this mathematical religion connect up with the space group symmetry?
Oh, you mean like in crystals?
The glide plane that a crystallographer would talk about in this, you haven't mentioned. I wonder if that's because you don't need to, because it's all implicit, or if it's because you don't care, because you're talking a different language with a different religion.
No, I think ultimately, I think it's the same language and the same religion, but here we're just confining ourselves to planar patterns, just for the simplicity of fitting everything in an hour, and also because it hangs together nicely, because this lets you describe all the symmetries you see on the tilings beneath your feet and the brickwork on walls and fabric patterns. It's sort of everything two-dimensional. It won't describe crystal symmetries for you. There you need to go to something that's truly three-dimensional.
I was saying I'm two-dimensional crystal symmetry. The glide plane that's in there is a two-dimensional crystallographic. It's a two-dimensional symmetry operation that I would use in classifying the symmetry operations that form a group.
Oh, you're thinking of just the translational symmetry?
Your central point,
Yeah.
which is the pinwheel rotation.
Yeah.
There are two glide planes that pass, two glide mirrors that pass through that point.
Oh, I see. You're interested in this operation?
The glide mirror means I do the mirror,
Yeah.
and then I translate up.
Okay, may I postpone your question because we're going to get to
Okay, good.
this operation here. In this case, I would say to give some answer, we don't need it here in a sense because the rotation explains it. And in any case, no matter how we choose to think of it, when you fold everything up so that every angel's wing matches with every other angel's wing, no matter how you describe it, that's the beauty of geometry. It sort of transcends language. No matter how you describe it, you've got to get this. And so then the question becomes, what's the best way to describe this thing? And Conway's answer, which I think is a good answer, is the best way to describe it is by saying it has a mirror reflector boundary. Along that boundary, it has one corner reflector. Well, it would if they lined up. It has one corner reflector, and it has one cone point. So it's a description of the folded form, whereas I think the crystallographic analysis often relies more on the unfolded form and is more subject to these discussions of, do we want to think this going to this? Do we want to think of it as this? Do we want to think of it as a rotation? There's more ambiguity, whereas here there's no ambiguity. You get one folded up form and bam, you write down a name for it. Okay.
Why do you have a glide plane? Doesn't it, it's not symmetric, right?
There
If
is
you
no
push
glide
the-
plane here.
Yeah, if you push the wing, the bottom wing up and flip it over, it doesn't match.
It's all oriented, it all has the same orientation.
Yeah, I think he wants to take this wing
Yeah.
up to here.
Here,
So I think there is a
strictly two-dimensional.
glide reflection in there.
All the way up there, okay.
Yeah.
But again, I think the philosophy here is rather than that we'd be wasting our breath to say, well, do we want to think of glide reflections, do we want to think of rotations, that we can save those discussions by just folding everything up till we just have one copy of the angel's wing and one copy of the devil, and then describe this thing and say, what are the salient features here? Okay.
Labor the point, but if you do that, then the sideways wings don't come out right.
Oh, okay. So you're saying in the bigger picture that if we took this up to here,
It works.
yeah, it looks good.
Yeah.
This is not, we're choosing different name, it's fine.
Yeah. And in fact, I think I'm actually kind of glad this digression came up, because I think it illustrates the beauty of going to the folded form, that you get into these discussions. There's a lot of ambiguity here and no ambiguity here. Okay. Yeah, exactly. Okay, so Escher's Angels and Devils is 4-star 2. And I think in the interest of having time to get out on the plaza here and look at some tilings, I'll skip this for now. In your handouts, you're welcome to take them home. So for the homework, you can work out the names for these 2 quilt patterns. Yeah?
Just ignore the fact that like those little rectangles aren't quite the same.
What should you ignore or not ignore? Okay, the boundary, the edge here, the border, you should ignore. Within here, if they're different squiggly patterns, ignore that. Okay, don't ignore that some are blue and some are not blue. Pay attention to that, but don't worry about the. Okay. Somebody was cutting this quilt out of a piece of fabric, and just think of them all as being the same. Good question. Thank you.
Yeah.
Okay. So let's organize here. Okay, so here's the wall pattern from the Sala dei Gigli at the Palazzo Vecchio in Florence. And actually, this is I repeated it on the computer, but this is actually from a photo of this thing, so it's legit. So here are its lines of symmetry. Now, the cyan line is a mirror line that you're familiar with from the cards and the honeycomb and everything else. So it just gives a mirror reflector over here. And our much anticipated glide reflection here, this magenta line is not a mirror line. It's not a line of mirror symmetry, but it does this glide reflection operation that, say we look at this magenta line and this fleur-de-lis, it takes it and moves it along and translates and reflects at the same time. So it goes flip, flop, working its way along, reversing the handedness each time. Okay? Now, what's cool, whoops, let's switch to the next slide. Okay, so with this glide reflection, if you have a glide reflection that's not a consequence of something else, then it has a really cool effect down in your orbifold here. So here's this basic rectangle I just made a copy of. Okay, it wraps around to make a band like this. Okay, and as I said a moment ago, that cyan line is just a mirror reflector like you're already familiar with. But the magenta line is really pretty cool because you can see most of the fleur-de-lis is here, but it's missing a little tip of this petal. That little missing tip is way the heck over here, 180 degrees away. So to glue things up along that magenta thing, you need to glue each point to the point 180 degrees away. Each point glues to the point directly opposite. Okay, if you would like to see this gluing happen, which to understand what we're doing today, you don't need to see it happen, but just for fun, if you want to, here's how it works. Okay, thanks to George Francis, who's a master of mathematical illustration. So we're going to start down here. Here's a circle. We want to glue together diametrically opposite points, or in the metaphor here, we want to zip them together. So we're going to start, say, by picking these 2 points. You can think of this as being most of the fleur-de-lis, and this as being the missing petal tip. So we'll take those 2 points, sort of pull them up a little so we can get going. Take those opposite points, move them together, start zipping. And as we zip all the way around that circle, our surface intersects itself, and we end up with the cross cap. Okay? But like I said, to understand what we're doing today, it's kind of fun to see this, but you don't really need to rely on that. All you really need to know is that along that magenta line, each point matches up with the point diametrically opposite. Okay, how do we write that down? Well, we have our orbifold has a mirror boundary, so we write a star, and then it has this cross cap, so we write an X, so the name is star X. Okay? Now, up until, okay, yeah, so there's the pattern. Star X is the name of the pattern there on the wall of the solid de Gilly. Up until, we're not going to do this example, until I got off the train this morning, I was thinking, well, I was preparing this talk, and I thought, okay, we'll do the names for all possible 17 groups. I thought, well, we might be a little pressed for time if we want to go out on the plaza. I'll skip the ones that don't have any mirror reflections in them, because almost everything you find has mirror reflection. And I got here, and there's all sorts of cool symmetry out there, some of which has no mirror reflections. So I don't have good graphics for it, but I want to insert an extra example here. You'll now, by the way, have the tools to identify all 17 groups. So that's another advantage. OK, how do we do it? Let's start this from scratch. OK. What's that?
You could have 2 cross caps.
You could have 2 cross caps. Yeah, something like this. It could be a cross cap on each side. The name would be XX. Yes. OK, so in an example with no mirror symmetry, okay, I'm just going to come in here, make a little scribble. And just for sake of seeing some contrast here, let me call up pen color, switch to a different color, and maybe make a scribble down here. OK, the basic fundamental unit in the printer didn't do too well with this, but the basic fundamental unit is this, which I made a copy of here. But note that this doesn't have any mirror symmetry, and in fact cannot possibly have any mirror symmetry, because if you look at this spiral, going from the inside out, it goes clockwise. And these other copies, they're rotated by 90 degrees, but they're all going clockwise. So you're never going to find any reflection symmetry in this picture. You're never going to find any glide reflections in this picture. So the question is, OK, we cut out this one basic square that seems to have one example of each part of the motif. But now what the heck do we do with it? Well, this spiral, which is one continuous thing, has been divided into 2 pieces. So we have to get it to match up with itself. So I'll bring it around and match it up with itself here. And then the same thing for this purple scribble, which is one thing, but is split into 2 pieces here. So we end up the orbifold, which is really more of an orbirolled than an orbifold. There's no folding going on, but it's still called an orbifold. The orbifold is this thing that looks like a little turnover, or a calzone, or a samosa, depending on your favorite cuisine. OK, so its name. There's not going to be a star, because there's no mirror reflector in this thing. OK, what do we have? What features are in this turnover? Yeah, we have cone points. We have 3 of them. And in fact, let's go back here. The green cone point at the center where this green spiral is based, how many fold rotation is that there? Yeah, 4 folds. So we'll write a 4 for that. We have another point with 4-fold rotational symmetry, namely where these purple ones come together. So we'll write a 4 for this. At this last cone point, this one's a little different because it's how many fold? 2. Great. So the name of this thing And I stuck in. John was wondering, why I was in a hurry to rush away from lunch, but this was why, to stick in an extra slide. So the turnover has group 442. Now, okay, I think we're about ready for our field trip. And I have to say I was delighted here that when I was getting ready, I said, okay, tell my wife, do some stuff in the lecture hall, then go out and find some patterns. She said, well, what if there are none? What if, all the walls are just drywall, the cement is just flat cement? You'd be in big trouble. Well, we'll hope something works out. And in fact, the Simon Center does not disappoint. So if you'd like to grab your stuff, we'll take a walk out on the plaza. Make sure you have pen and paper available, because this is serious work out here. We have like 4 or 5 symmetry patterns to identify.
Is there a way to see that there are 17 by counting stars and asterisks?
There is, and in fact, I'm going to get things moving out here, but let me take this on. Leave it on. Okay. Oh, sure. Oh, you're going to get it. Okay, sure. I'll leave it on. Okay, so let's go outside and we'll analyze some of these things, and I'll bring my notes for that. And there's a reason. Oh, sure, yeah. If anybody wants extra copies, help yourself.
So some eventually ends up canceling? Is that what happens?
No, what happens is, and this relates, where's this other guy who was asking the question? This relates to your question as well about, why are there only 17? You're saying, what if there's more than 2 crosscaps? The answer is there are a lot more than 17 patterns, but they're not all flat. And in fact, when we go back to the lecture hall, I have some slides of Escher's angels and devils on a sphere, and another angels and devils in the circle limit picture, which is hyperbolic. And the correct statement is that of all the possible patterns, there are 17 flat ones. If you want to have 3 cross caps or lots of comb points, you can do it in these kind of circle limit patterns or on a sphere.
If I take the ratio, the area of the crystallographic units over the area of the orbital,
Yes.
doesn't that give the dimension of the point group?
Probably. My grasp of point groups is small, but that's sort of the amount of freedom you have, ignoring fancy translations you need to account. Okay, so what I think I'll do here is maybe as a group we can go around and just see the different sites here, and then you can break up into your little groups and work out the names. So the first exercise, the simplest one, is beneath your feet. So if you look down, the square tiling in the plaza here is an easy one to get started with. So for all of these, by the way, your mission is the same as inside, to figure out what the orbifold is and to figure out what the name of the pattern is. So example 1 is the square tiling here. Example 2 is the brickwork, the red brickwork in the math tower there, the standard brickwork. And that's kind of a medium level example. It's a group you haven't, this one is one you've seen this morning, I believe. The bricks over there is one you haven't seen, but the same principles work, so you can work out the name. The yellow bricks are the same pattern. Okay, if people could continue down onto the steps, but not beyond here. We'll look at them next. You're filming too. Okay. So the third example is the tiling in these little landings, which is like standard brickwork, but it's made with parallelograms instead of regular bricks. So a question for you here. What are the mirror symmetries in this?
These are never.
There are none.
None. Right. Okay, so there are no mirror symmetries here. Otherwise, it's like standard brickwork. When you analyze this one, I think we can permit ourselves a little simplification. They made some skips here, I think, to accommodate these central poles. So the pattern goes along, and then there'll be a half one. It's just, pay no attention to that. Pretend it didn't happen, and just pretend the regular parallelogram pattern continues. Okay, come on down here, please.
Must have gotten really excited when you saw the head.
Yeah. So, but we're not there yet. Okay, so for the fourth example is on the wall of the fountain here. You can see it's kind of like standard brickwork, but the bricks aren't the bricks are staggered differently. It's no longer half a brick length. So a question here too is, where are the mirror lines in there? No mirror lines. Okay, so it's something else, but again, it's doable. And then, every exam has a trick question, right? If you want the trick question, here it is. Have a look. Think about it. Enjoy it. Don't spend too much time trying to work out the name. Okay, so please go ahead and split up into groups and try to find the names of some of these for as long as you dare to stay and do so. And I think I'll just mill about and see whether people have questions. Actually, Bill, pardon me for about 45 seconds. I'll run inside, get my long sleeve, come back out, and go around and see whether people have questions. When you are analyzing this, remember these patterns, it's a tactile experience as well as a visual one, so unless the management has objections, feel free to come on into the fountain and stick some tape on here and analyze.
Turn the fountain on.
Anybody want to take this?
a little bit.
That up? Anybody make a tape taker? Okay.
A lot of fun today. And to think about 3 dimensions is looking at 7 o'clock. This was the good one.